Okay, in the intermission, I corrected my slide. So 1 to n relationship, one person, many passports. We can put the person ID as the foreign key in the passport table. Yep, that's how we implement that relationship. So in this case, the relationship gets turned into a foreign key, primary key, foreign key pair, no new table. If we've got end-to-end relationships, you need a connecting table, basically, with whatever constraint set, or the required constraint set. Okay, constraints on columns. The two main ones, or the two sort of universal ones, well, two main constraints are the unique constraint and the not null constraint. So the unique constraint just makes sure that every entry in every row differs. So you can't have the same entry, same value in 2 rows in a column with a unique constraint, except if it's a null value. So you can have multiple null values, but if it's got a not null value, that must be a unique value. If you try and insert a row with a non-unique, non-null number, the database says no go, throws an error, tells you can't do it. The other one is not null. Not null simply says exactly what it says on the till. You can't put null values in a column. A primary key is a combination of unique and not null constraints. That's how a primary key is implemented. In Postgres, there is a function just to implement a primary key, but you could create a primary key by creating a non-null and then a unique key, and a unique and a non-null. The foreign key references another column in another table, and if you remember, foreign keys must, the value, the foreign key must exist in the column in the other table or be null. The other column constraints are the check constraint, and the check constraint implements a domain. Okay, so we're now going to look at some different ways in which domains can be implemented. So remember, a domain is the range of values valid values that can be put into a field. And there are a number of ways that domains can be implemented in Postgres and indeed other databases, but I can't guarantee that all the ways I'm going to show you here are implemented in other DBMSs. So one thing you can do is do a check constraint on a column as part of the create table, the table definition. So here we've got a table called products with 2 fields, product number, and some kind of name, the name of the product, text field. And the price, oh, we've got a third column, third column price, which is a numeric field. And we have a check constraint imposed on the price field that says that the price must be greater than 0. It has to be a positive price. Now maybe it should be greater than or equal to 0, then we could have a price of 0. But we can't have a negative price is the important thing here. So every time a row gets entered, this check constraint gets checked on the price, and if the price is 0 or negative, the row insertion gets rejected. So that's quite simple. And these constraints can be more complicated. So here we've got same table or slightly increased table. We've got a check on the price that is greater than 0. And we've then got another field called discount price, which is, and again, a numeric. We've got another check constraint on this, that the price has to be greater than 0. Okay, so that's just reiterating that. And then we have a constraint here called valid discount. This is the name of the constraint. And the name of the constraint, the check function operation that implements this is that price is greater than the discount price. So you couldn't enter in a row in which the discount price is greater than the original price. That sounds reasonable. So we have to check the price is greater than 0, and then we can check that the original price is bigger than the discounted price. So that's one standard way to implement constraints. Constraints are a domain constraint on the values that can go into a field. Often one of the things, the constraints and types of constraints that we want to implement is what's called a lookup list, basically. Or you've got a set of values, a nominal set of values for a field. Say colours, green, blue, red, yellow, violet, gold, but you're not going to accept indigo. Okay, so you have a list of acceptable values for a field. And there are 3 design options that I've come up with or standard design, easy design options in Postgres for how you might implement such a constraint on a field. So a list of acceptable values. For example, we've got an example here. We're only going to allow valid continent names. Okay, so I think we mentioned this previously in one of the previous SQL ones. So we've got this table country, which has a whole load of fields, and then it has this field code, which is a country code. Sorry, it's not null. Below that, sorry, we have a consonant. Sorry, we have this field consonant up here. So we have our field consonant, text field, and it's not null, column constraint on it. Down here, we define a constraint called country consonant check, and that is a check constraint on that goes through this set of constraints each time a row is entered. And as you can see, we've got a list. Continent equals Asia, continent equals Europe. We're having to remember to cast that to a text for whatever reason, or Europe, or North America, or Africa, or Oceania, or Antarctica, or South America. So in our table definition, we've defined a check constraint that checks that it's a valid consonant. We've seen that before, nothing new there. Here's an alternative, and that's to create a domain object, which is a user-defined data type. So you're defining, in this case, a data type that only will accept that list of values. So in Postgres, we can create this domain. So we create a domain, and we call that domain consonant name, and it's as a text domain. And it has a check that the value, a check constraint on it, that the value is in Asia, Europe, North America, etc., our list of continents. And then when we create our table country, here on the consonant, where we define that the field consonant, instead of the consonant being a character field, it is now a field type consonant name. Okay, you clear what the difference is here? We've created a new data type called consonant name that only accepts these values, and then we're defining the field to be of that data type. You understand the difference between that and the previous ones? The previous one, this list was defined in the table definition. Now the list is being defined in a user-defined data type or data domain. The final approach is to use a foreign key, a primary foreign key relationship. So here we've got table consonant, ID primary key, name. Okay. So we have a table of consonants. And in each row, we put one row for each of our consonants. Okay, we probably should have had 1, 2, 3. Okay, so that's obviously while I wrote this, I didn't actually implement it because that would have failed, but that should be number 2, that's number 3. So then when we define our table country, our consonant field is now an integer. It's not a text because we're looking up the ID. We're looking up the ID. Why do we look up the ID rather than the text? It's because it's a lot quicker to look up numbers than it is to look up strings of text and to match strings of text. So quite often what we tend to do is to match on these ID values rather than doing a string match, because an integer match will be much, much quicker than a string match. Okay, so that is a consonant, it's an integer, and it references the consonant, the ID field in the consonant. And then when I want to get the consonant that a country in, then I write a query that returns, that does a join onto the consonant table and returns the name field from the consonant table to give us the name of the consonant that the country is in. So that's 3 different design options that you could do for a lookup table. Which one you choose, again, depends on the circumstances. So the consonant of mu has just been discovered. If you're not aware of the consonant of mu, there it is. It's one of these legendary consonants, again, along with Atlantis and places like this. If you remember the band, the KLF from the 1980s, you're probably all a bit young from the up. They had a song called Moo Moo Land. Well, this is Moo Moo Land. This is Moo Moo Land. It's a place where wondrous, high intelligent, historic civilizations have existed and then been wiped away, and of course we know nothing about it. Anyway, there it is. The island, the continent of Mu has just raised itself out of the atmosphere, out of the ocean. Okay. Now, if we implemented check and domain constraints, the first 2 types of constraints, then we would need to update the whole database object to include a new consonant. So we'd have to update our table definition with the first example, with the check constraint in it, or we'd have to rebuild our domain object if we used a domain object. However, if we did the third option and just had a lookup table, which is slightly more complicated in that you've got to manage 2 tables and a query between them, a user just needs to add a new row into that table to add the consonant of mu to the available consonantal lists. So if you think you're going to need to add new things to your list, then the lookup table is probably the best way to go with a table, the third method. However, if you're reasonably fixed with your constraints and you can't really see it having to add new constraints on, then one of the previous 2 approaches would probably have been more appropriate, because you don't need a special database manager to go in and update the check constraints. Here, you can just implement it so a normal user on the interface can add the new consonant. All right, normalization. Oh, we've got to move. Okay, normalization, right. Remember data redundancy. One of the whole purposes of the relational model is to get rid of duplication of data. It's one of its purposes. Reduce the duplication of data, and duplication occurs both within a table and across tables. So you might get duplicate data information in the same table or in different tables. Why do we care? Well, it slows waste space, bigger databases, slows querying, so it has a detrimental effect on the system working itself, but most importantly, it's about maintaining data integrity. If you've got more than one copy of the same data item throughout your database, you've got to update all of them to keep everything in sync and to prevent what we call database anomalies. So we'll run through these anomalies really quickly. So there's 3 types of anomalies, if I remember correctly. I might discover that there are 4 as I slip through the slides, but I think there are 3. The update anomaly. So here's a little table. Remember the table definition, employee skills, 3 columns, employee ID, address, skill. So an update anomaly, and I have to think carefully about these, is a data inconsistency that results from data redundancy and partial update. That's the definition. It's not easy to understand. If an employee has multiple skills, so in this table, if we employ and multiple skills, and their addresses change, so you would have, for each employee, you would have to have 1 row for each skill, and the address changed, you would have to update the address in more than one row. You'd have 3 rows to update for addresses to maintain consistency in your data. Yep. So if I have 3 skills, I've got 3 rows for the employee. Each row has an address, has data redundancy. There's data redundancy in the address. I would need to update all the addresses for my data to remain consistent. And an update anomaly occurs when not all rows are updated. So if I just end up the one address row, one of the rows gets updated, but the others get missed, we've got an update anomaly. So we're trying to avoid these update anomalies. Insertion anomaly. Oh. Insertion anomaly. An insertion anomaly, I missed the word out, is the inability to enter data when some is missing. Okay, or in other words, data cannot be inserted without the presence of other data, even though we might want to. So there's a constraint that all faculty must teach on at least one module. So module code has a not null constraint set on it. A new faculty member's just been hired, but not allocated to a module. So we would need to, under this stage, we'd need to enter null in the module code, but that's not allowed. This leads to an insertion anomaly because we've got information on our new faculty member, but we can't enter it because we don't have certain information as required in the model. Now you may be saying, well, just redesign your model. Yes, of course, that's what you do. But this is an example of an insertion anomaly. The problem is the database design. That's exactly the problem that we're trying to avoid, is this database design problem. Bad design prevents us entering the information we have in the absence of all the other information. The final one is the deletion anomaly, which is the unintended loss of data due to a deletion. So you want to delete some information, but you're having to delete other information as well because of the bad design. So in this case, the faculty member is on sabbatical. They've gone away somewhere else to do some work, write a book, something like that. So they're not teaching on the module. So we have to delete. We want to delete the module code, but we can't. And the only way we can get rid of the module code associated with this person on the faculty is to delete their entire faculty record, which is obviously, so we're deleting data, as in these 3 fields, because we want to delete this. So the module value code can only be deleted by deleting the entire record. It forces us to delete data that we shouldn't have to delete to get rid of data that we do want to delete. Okay, so we're trying to avoid those anomalies. So normalization gradually reduces data repetitions in a table through the creation of several increasingly more efficient compact relations, which go according to some kind of normalization form. This generates an efficient design for the managing of data integrity, avoiding insertion, deletion anomalies. There is a danger, though, normalization can lead to complex designs that are slow and difficult to program. So there is a trade-off here again between redundancy in data and complexity of design, which may... Okay, so there's 3 forms of normalization that we need to consider here. There are in fact loads of others, or quite a few others defined. I don't know anything beyond the 3rd normal form, so don't ask me what 4th normal form is, I have no idea. Okay, so Codin defined the first 3, which are what we're going to go through. First normal form, all relation attributes. In all relations, attributes contain a single unrepeated value. If you meet that criteria in first normal form. Second normal form, all fields within the relation are dependent on their key fields. I'll go through these. Third normal form, all key fields in the relation are mutually independent. So, examples, always have an example. These are much more easy to understand with examples, and of course we're going to have a practical where we're going to do this. I'm going to give you a table, you're going to normalize it this afternoon. Okay, first normal form. Each field contains a single unrepeated value. So there are 2 cases here that I'm going to give you. The first one is where the information is different, and the second case where the information is the same. But there is more than one item of information in a field. So here's an example. a name field, John Henry, Abigail Josephine Winsome, 2 names. Okay, is this a repeated value? Well, are there multiple values in this field? Well, it depends what you think a name is to start with. And if you go to the W3C recommendations for name fields, which is an exciting read, I can tell you, what names around the world, I never realized how wonderfully varied they were. And that certain cultures don't have things like surnames. Names are related to geographical locations like towns, and how wives' names and husbands' names have different forms and all this. So when we see 3 fields that say first name, middle name, surname, or given names, whatever, that is a cultural reflection of the Western world, and particularly Britain, unsurprisingly. Anyway, so in this case, let's say that we want to split the name apart. WC3 actually talks about treating names as single fields, and they regard that as if you're doing a global database of names for people all around the world, that a single field for name is probably the best way to go. Anyway, okay. So in this case, we've got forename, first name, surname. In this case, we've got a middle name as well. So in this case, they're different types of data. They're all names, but we can say this is a forename or a first name, a middle name, surname. We can break it apart simply into different fields. Not exactly, it's pretty straightforward. Just break it apart. However, sometimes you get, this is perhaps the more classic example, where the same type of information is in the field. Okay, so in this case, we've got module, GS, whatever it is, course, student, and it's a comma-enumerated list of students on the course. Okay, department GGP. Okay, so this is not in first normal form, as there is duplication, more than one item of data in a field. So we need to break it apart. So what we do is we have to create a new table, and the reality is this is not actually a table about modules. It's actually a table about students. Okay? It's telling us that these 2 students are taking this course. So despite the fact this is ostensibly called a table about modules, the reality is that a lot of the data in this is about students taking modules. So what we need is to create a new table in which the duplicated values become the primary key in the new table. So we've got 2 students here, so we want 1 row for each student, and obviously the primary key is not the name, because names can be repeated. It's in fact the ID of the student. Each student is now on a module. So it may look like we've got lots more data in here. We've got, if we counted the number of characters, we've got a lot more characters involved, but we've now separated, and we can understand an SQL query to work out which student is taking which module relatively easily. Here, we need to do some string processing to separate out the individual names out of this list. So if we've got duplication, we either split, if it's different information, we just split it into different fields. If it's the same information in the same field, we duplicate down into rows, and the table is in fact about something else. Second normal form, all fields must be exclusively dependent on the key fields. So we've got this is a table on parts being supplied to various companies. We've got a supplier, the key is supplier number and the parts number. That's the primary field. So all fields must be exclusively dependent on the key field. So all fields must be dependent on both supplier and part number. Now, city, so city is a non-key field, but it is only So a city is where the supplier is, and the status is where the city is that the supplier is providing. So it's UK or EU. So we're post-Brexit already here in this table. We're looking forward. So the city is where the supplier is. It has no connection to part number whatsoever. So it is not dependent on the primary key. So this table is not in second normal form. It's only dependent on only one of the fields defining the primary key, i.e. supplier number. The relation is not into second normal form. Is everyone clear on that? Anybody unclear on that? Yep. City is not dependent. Indeed, status isn't either. Quantity is dependent on both part and supplier, though, probably. Okay, so what do? We take that relation and we split it apart into two new relations. And in this case, what we do is we've got a list of suppliers and we've got a list of orders. Okay, so the city and the status are both just dependent on the supplier. So we have a supplier table, primary key. Now this cities and the status is dependent on who your supplier is. Both non-key fields are only dependent upon the supplier number. Over here, the quantity that need to be shipped depends on both who you're getting it from, or who you're ordering it from, and the part number that you want to order as well, and that quantity. So by splitting it apart, we've now got from one table into two tables. We're now in second normal form. It's quite easy in theory. This practice is a little more complicated, though. Third normal form. So a table has to be in second normal form before it can be in third normal form, and all the non-key fields are mutually independent of each other. They must be mutually independent of each other. So they must be dependent on the supplier ID, but independent of each other. So in this case, status is dependent on city rather than directly on supplier. Okay? The supplier may be in a city, but the status of the city depends on the status is dependent on city rather than directly on supplier number. And both are non-key fields. That's why it's not in third normal form, because these are non-key fields and status is dependent on city. So again, we split it into two tables. In this case, we've got the city, status city, status city. So in this case, the city is the city number. Both tables in three. City status and city are dependent on city number, and city number becomes a foreign key in the order table. This should be order rather than supplier table there. Okay. All right. Okay. So we split apart like that. So we split the cities apart from the supplier information. So we're going to have an exercise where you're going to go through third normal form. It's one of these things that when explaining it, I think doing it is far more better for learning than explaining it. Anyway, okay, quickly. We're nearly finished now. Denormalization. Okay, so most databases, relational databases, approach sort of try and be normalized to third normal form. Rare. I think it's rare for anybody to go any further than the third normal form, but I think the other higher forms are more theoretical than practical in many cases. But when you go out and look there and download data and go and look at databases that have been implemented, a lot of them are not normalized very well, or normalized, not normalized at all. And why is this? So this is the reality of it. That's the theory of it. Everybody makes a nice third normal form database and everything's good and dandy and no duplication. But the reality is somewhat different. So the first point is about normalization, is about maintaining data integrity. That's the whole point of it, is to avoid this data duplication, to maintain your data integrity. And that's really important if you're entering lots of new data, updating data, and you need to keep that data, the integrity of that data. That's really important. However, if you're effectively, you've got a read-only fossilized database that you're not updating, there's no updates that are going to ruin your data integrity. So it may not be fully normalized, but to a certain extent, so what? You haven't got a problem of maintaining integrity. The data is as it is, so to speak, which may not be fully normalized, but you can work with that.
What was the read-only system?
A data warehouse. So, for example, so I built this thing called the Entangled Bank. The Entangled Bank has lots of information on mammals. It was built once. It's unlikely, nobody's entering in new data on a daily basis. It was built, it's out there, it's static. Now I could go back and I could update the data and if new data was available, but it's not happening. So effectively it's a static database, and probably a lot of the databases out there are static in many ways. Other thing is data warehouses. So we'll talk about data warehouses in due course, but say you've got a huge transaction system about all your sales, and then you sort of summarize that into what's called a data warehouse, which allows you to look for trends over large periods of time. It's separate from the business, the day-to-day business of making sales. It's a historical fixed database that allows you to query trends in sales through time and things like that. So that would be an example of a relatively read-only system. Efficiency benefits, as denormalization can query performance. So we've had this constant tension between complexity of our data model and maintaining integrity versus how difficult it is to actually do things with a complex data model and how slow complex data models become as data volume increases. So some of these new or the NoSQL models were direct responses to poor performance of relational models, normalized relational models with large data volumes. So denormalization can improve query performance so that may be a reason simply to make the system operatable. Limited resources, okay, again, simpler models are easier to understand and develop than complex models. Full normalization of large databases is a big job. There's a lot of time, design time, a lot of programming effort to implement these things. And not worrying so much about normalization can result in a simpler model that's easier to develop and gets the results, basically. And finally, I highlight ignorance. Systems are built by all kinds of people with all kinds of histories, many of which have never sat in a class on database design in their life. So a lot of systems, particularly small ones made by students, made by research scientists and things like that who are discipline experts, they never even heard of normalization when they created their data sets. So there are all these reasons why denormalization might work well. We'll won't worry about that. That's an example of a denormalized what's called a star schema for data mining. We meet data mining in a later lecture. All right, to finish off. So that's our physical model. So last year, I realized that students were doing two kinds of things. To a certain extent, this should be part of the assessment talk, which I'll give in when we go up to the lecture, up to the practical. There were two ways that logical models are used. Okay, going back to logical models. One is you start off with your logical models, you're drawing your logical models, as a sort of mirror of the world as I see it. You're trying to understand the entities that exist in your system and what their relationships are. You're taking a real world environment system and you're saying, how do these connect together? What are the entities in the system? What are the relationships? Then there is the database mirror view of the logical model, or reality of the logical model, which is that the entities and relationships, which model shows the entities and relationships, that they're actually implemented in the physical model of the database. So in this case, your ER diagram is modeling the things in the world that you're interested in. In this case, they are representing the structure of your database as implemented. But for many students, they don't kind of quite manage to move from what they'd like to create, or they think they should create, to what is actually created. And I think it's not just students that you see examples out there if you Google ER diagrams and things like that. Often there's this implementation gap. So there's almost two logical models. There's the logical model of you think the way the world should work, and then there's the logical model of how your database does work. And when you include your logical model in your assessment, as part of your assessment, you need to be clear, or it needs to be clear to me, whether it's a model of what your database is, that you've implemented, or whether it's a model of the world, and what the difference is, what this gap is. What would you like to, what have you not managed to implement about your model of the world in your physical model? Okay, so bear that in mind. There is this difference. Okay, just to summarize, physical design, we know, implementing a model, logical design, a relational database model. Logical modeling provides tools that are used for two purposes. This is what I've just been saying. Understanding the data and constructing a design. So that's the first purpose. That's my world mirror, logical model. Understanding the data and constructing design. And two, documenting system design. So it's got two functions, these logical models. But it's often unclear to me whether a logical design is about that, or or preferentially the two are actually the same. That's what you're aiming for them to both be an understanding of the data and the construction of the design and documenting the system design as it is. But because there's this implementation gap, they're not always the same. Okay, so bear that in mind. Is your logical design in your assignment one or two, or a mixture of the two? Okay, physical design involves the conversion of ER entities into tables, fields, and attributes. Design rules and normalization, we know that.